microscopic crack, which grew in both directions at about 3 miles per second. The crack, following the path of least resistance, encircled the globe in about 2 hours. As the crack raced around the Earth, the overlying crust opened up like a rip in a tightly stretched cloth. The subterranean water was under extreme pressure because of the weight of the 10 miles of rock pressing down on it. So the water exploded violently out of the rupture. Calculations show that all along this globe-encircling crack, fountains of water jetted supersonically over 20 miles into the atmosphere. The spray from this enormous fountain produced torrential rains such as the Earth has never experienced before or after. The Bible states that all the fountains of the great deep burst open on one day. And it describes these events about 4,500 years ago, which we can now tie together scientifically in cause and effect order as the hydroplate theory. The fountains of the great deep and the expanding steam produced violent winds, some of the water jetting high above the cold stratosphere, froze into supercooled ice crystals and produced some massive ice dumps, burying, suffocating, and instantly freezing many animals. The high-pressure fountains eroded the rock on both sides of the crack and even threw up the limy contents of many pre-flood seas. Huge volumes of sediments settled out of this muddy water all over the Earth. These sediments trapped and buried plants and animals, forming the fossil record. The flooding uprooted vegetation, moving it to regions where it accumulated and quickly became coal and oil by processes we can duplicate in the laboratory today. Experiments show that as erosion widened the rupture, its width became so great that the compressed rock beneath the subterranean chamber sprung upward, giving birth to the mid-oceanic ridge that wraps around the Earth like the seam of a baseball. The continental plates, the hydroplates, still with lubricating water beneath them, slid downhill away from the rising mid-Atlantic ridge. After the massive, slowly accelerating continental plates reached speeds of about 45 miles an hour, they ran into resistances, compressed, crushed, thickened, and buckled. The portions of the hydroplates that buckled up formed mountains. Those that buckled down formed ocean trenches. This is why these features are generally parallel to the oceanic ridges from which they slid. The hydroplates, in sliding away from the oceanic ridges, opened up very deep ocean basins into which the floodwaters retreated. Every continental basin was naturally left brimful of water, producing many post-flood lakes. Each lake that grew from rainfall or drainage from higher elevations spilled over its rim at the lowest point of the rim. That eroded a little notch in the rim, allowing even more water to flow through the notch faster, cutting the soft flood-deposited sediments even deeper. This process accelerated until all the lake's water dumped through a very deep slit, forming a canyon. The largest of these was the Grand Canyon. North and east of the Grand Canyon was a huge lake that I have identified and named Grand Lake. Its dumping released more water than is in all 5 of the Great Lakes combined. Grand Lake spilled over its rim, eroded its dam, 20 miles south of Page, Arizona, catastrophically forming the Grand Canyon within a few weeks.
Rapid deposition of flood deposits from tidal action means there was little time for erosion to occur between successive layers. On the long time scale envisioned by evolutionary theory, there should be considerable evidence found of erosion and infilling by successive geologic formations during the weathering expected over millions of years. The geological layers of the Grand Canyon are remarkable in showing little or no evidence of erosion between different layers. Instead, we see pancake layering, very much consistent with the rapid deposition envisioned by the flood model. Erosion did not occur until all of the layers had been deposited. But how rapidly could the canyon itself have eroded?
Freshly laid down sediments would still not have completely hardened into rock, which allows the possibility that erosion of the canyon could have taken place far more easily than if it had hardened into rock, as evolutionary theory has assumed.
However, under the right conditions, water can rapidly cut its way through the hardest of rocks, such as the granites at the bottom of the Grand Canyon. Those conditions involve cavitation.
Cavitation is the rock pulverizing process associated with water flows greater than 100 feet per second. As water detaches from irregularities in the bedrock channel, vacuum bubbles are produced, inflicting hammer-like blows on the bedrock surface, literally converting the rocks into powder.
A modern example of rapid erosion of bedrock from cavitation comes from Glen Canyon Dam on the Colorado River just above the Grand Canyon. Excessive snowfall from the high country of the upper Colorado River Basin in late spring of 1983 caused excessive runoff that poured into Lake Powell at rates of up to 148,000 cubic feet per second. This rapid inflow threatened to overflow Glen Canyon Dam. To control the high flow rates, the power plant was run at full capacity, releasing 28,000 cubic feet per second through the turbines. Then the outlet tubes were opened to drain another 17,000 cubic feet per second. This was still not enough. The emergency situation required engineers to risk damage to the spillway tunnel. And on June 15, the 40-foot diameter left spillway tunnel was opened to drain an additional 13,000 cubic feet per second, which was then raised to 17,000 cubic feet per second. Then on June 28, the flow was increased to 32,000 cubic feet per second. At this point, the water exiting the tunnel became red, and noticeable ground vibrations, earthquakes, were felt by engineers. Large blocks of concrete and bedrock came hurling from the 40-foot diameter tunnel. After closing the spillway tunnel, the survey team discovered extensive cavitation damage. The 3-foot-thick steel-reinforced concrete lining of the tunnel was penetrated by huge pits. At an elbow where the tunnel levels out, a hole 32 feet deep, 150 feet long, and 40 feet wide was cut through the lining into red sandstone bedrock. This hole required 63,000 cubic feet of concrete to fill. The repair process to the enormous hole shows the vast extent of the damage. The speed of erosion in the Glen Canyon Dam spillway tunnel occurred very rapidly during the period when the red color of water appeared and ground vibrations were generated. It is possible that cavitation was pulverizing concrete, steel, and sandstone at the rate of 1,000 cubic feet per second during the peak period of erosion. The destructive effects of cavitation at Glen Canyon Dam tell us the Grand Canyon could have been eroded very quickly by the sudden release of a huge volume of water above the canyon. But where did the water come from, and what caused its sudden release? Dr. Brown's studies on the Grand Canyon provide one of the best answers.
Most people are told that the mighty Colorado River carved the Grand Canyon over millions of years. But if people could study the canyon from an aircraft, they could see its vastness and how tiny that river is in relation to the canyon itself. There is no river on earth that could carve this big hole in the ground, even over billions of years. If the Colorado River carved the Grand Canyon, the first question we should ask is, where did all the eroded sediments go? There should be a very large river delta at the end of the Colorado River. It's not